All right, let's start our discussion again. And here, let's just review a little bit of the details of the vectors. Um, for example, we have 2 points, point P and point Q, and we are constructing this vector starting from the P and stop at the Q. So it's PQ with arrow on top. How do we get the position vector? And we want to have this point Q to subtract point P coordinates, and then we'll get so 0 minus 5 as the x component, 1 minus 2 as y component, and a 6 minus -3 as a z component. So we have -5, -1, and a 9 as the position vector for this PQ. Remember this position vector we're getting here is assumed to start at the origin and stop at the point Q prime, which has the coordinates -5, -1, 9. All right. So those are the procedures for us to determine the position vector if we know the head and the tail. And there are properties about the vector we discussed in previous sections. And one of them is so-called the scalar multiple, which is we multiply one scalar to a vector. All right. So that is indeed give us either compressed or stretched vector along the original vector direction. Okay. Another thing we should remember is how do we compute the length of a vector? If we know this vector is having three components, so in the three-dimensional space, the length is denoted by having vertical lines on both sides, and the actual calculation is done by this. Okay, so here our example in terms of vector PQ we computed above will be the length is square root of -5 squared plus -1 squared plus 9 squared, which is 25 plus 1 plus 81, which is square root 107. Okay, so one important aspect about the notation we are using here and in the future is that if we use parentheses, this refers to a point, and if we use the pointing bracket, that actually refers to the position vector we should get. Okay, so those are the things we should always remember and be familiar with, and let's not forgetting about the difference between this pointing bracket and the parentheses. All right, as we discussed in previous section, we also talked about the unit vector, right? And there are special unit vector we want to remember that they use, and they are I, which is pointing to the positive x direction, and J, this is the positive J direction, and the K, this is the positive Z direction. Okay, and one thing we did is that we claimed that for any non-zero vector U, we can always find the unit vector along the direction of this U. And but for example, with this U equals 3, 4 as the component of the two-dimensional vector here, the length of this U vector will be 3 squared plus 4 squared under the square root. Okay, which is 9 plus 16, which is square root of 25, which is 5. So we use the notation E to indicate the unit vector, and the subscript U to indicate this unit vector is a line on the direction of U, and that is obtained by dividing the original vector U by its own length, which is, I think we should know the length already, which is the 5. Okay, so this is a scalar multiple. We are just multiplying these the scalar 1 over 5 to the vector. So this is a scalar multiple for this vector. We want to compute, and this is our result. All right, so this is the unit vector on direction of u equals 3, 4. So this is how we memorize it. And maybe you guys already noticed, I use this notation and this notation and this notation to indicate the special unit vector. And one thing we noticed that this I is only having 1 on the x, and j is 1 on the y, and the k is 1 on the z direction. So in terms of writing down or formulating the vectors, we can use the notation ijk to write down this vector. But this discussion is a little bit trickier than it looks on the surface, because sometimes some people may want to mix this position vector in the standard form using this pointing bracket. So this is the standard form. So far we are talking about. We can break it up as this vector plus this vector plus this vector, because the vector notation and the operation of summation for the vector is just adding the corresponding components. And naturally, we can see this one is A times the unit vector I plus B times unit vector J, and plus C times unit vector K. Okay, because what we should have is this is A times plus B times 0, 1, 0 plus C times 0, 0, 1. Okay, you can use either this or this. They're equivalent. You can use either way, but you cannot put ijk in here. If you want to use the bracket, the 3 numbers you are writing down here have to be a scalar. You can't use put ijk there. Okay, this is very, very important. All right, let's just practice a little bit of using the ijk to represent this vector. So it's very easy to write. This is a 2. If you want to follow the same procedure, you can do this. All right, and then this is a 2 times I plus -1 times j plus 6 times k. So here, only when you use ijk, you use the plus or addition, right? Okay, and then similarly, this is -4, 0 plus 0, 2, and because in 2-dimensional space, the I and j, the unit vector, will only have 2 components. This is what we're supposed to have, and then for this 2-dimensional vector, -4, 2, we can write it this as -2 times I, and then plus 2 times j. Okay, So this is a notation, and with those notation, all those are relevant concept and discussion. We should feel familiar with the vectors. And now let's look at something that is especially designed or defined for this vector. Okay, so a moment ago we discussed the scalar multiple for this scalar times this vector. We know the length, and also we know different notations. But now we are looking at something that is really just special for a vector. That is the operation, so-called dot product. So how do we carry out the dot product for two vectors? Let's just look at the general definition. So if U vector is having three components and a V vector is having three components also. Okay, so what do we want to do over here? Oh, I think I already have it here. We use V and a W. Let's just stick with that. All right, and then the dot product of those two vectors, and particularly this dot is a special operation defined for these two vectors, and the dot product of those two is obtained by multiplying the corresponding components of each vectors, and then the product will be summed up together. Okay, so one thing we can think of is that if this V vector is 1, 2, 3, and this W vector is indeed 4, -1, and 5, and how do we compute V dot W? Well, remember, it is corresponding component multiplied together. Okay, so they will multiply to each other. So it's 1 times 4 plus 2 times -1 plus 3 times 5. So this is what we're going to get. The result will be a scalar. It's 4 minus 8 plus 15, which is 11, I think. Oh, is that 11? No, sorry. This is not 11 because we made a mistake over here. This is 2 minus -1 is 2. So this is 17. Okay, this looks better. And we should note dot product of two vectors is a number. And this is a very, very important property we should memorize. Okay, and the second important message we should learn about the dot product is that the dot product of vector to itself should be what? We should compute it. Okay, so V dot V itself is ABC dot ABC, which equals A times A plus B times B plus C times C, right? Which is A squared plus B squared plus C squared. And we should see this is nothing but the length. Well, what I should do is I should write this as the square root of A squared plus B squared plus C squared, and then squared. Okay, then it is equivalent to say we don't have the square root and the square, but this is meaningful because under the square root, with this square root, we have the length of the vector v. So what we should be clear about now is that the dot product of a vector to itself is just giving us this length of this particular vector squared. So this is the second important message about the dot product we should memorize. Okay, so let's just move on. There are some special properties. We already talked about them. So this is the the second one we just mentioned. And this one we didn't mention, but it is quite obvious. If we compute the dot product of u and v, or we compute the dot product of v and u, so they should be the same number. And if you have any zero vector to dot with any other vector, you should get a 0 as the result. Okay, so why do we care about this dot product? Actually, this dot product is closely related to some of those geometric information we should be really careful about. And here's what we want to say about the so-called law of cosine. Okay, for any arbitrary vectors, v and w, right? We can define the angle between the two vectors as a theta, and then the dot product of those two vectors is indeed given by this. So the length of the first vector times the length of the second vector times cosine of the angle between those two vectors. So this is what we say about the law of cosine. Or another way to explain this is that the cosine of the angle between two vectors is indeed the dot product of those two vectors divided by the length of the first vector and then the length by the second vector. So this is very important geometrically because we can list the short discussion here. Theta is the angle between v and w. So obviously, if cosine theta is bigger than 0, which means the dot product. Why that? Because cosine theta equal to the dot of u and w divided by the length of those two vectors, right? So the length of a vector is always positive. So if cosine theta is bigger than 0, then the dot product of those two vectors will be 0. So vice versa, right? So if the dot product two vectors is bigger than 0, then the angle between theta for the theta will be between 0 and pi over 2. And on the other hand, if cosine theta is less than 0, this means the dot product will be strictly less than 0 also. This means the angle for the theta will be between pi over 2 and pi. And there's only one special case, obviously. So what happens if the cosine theta, which is the angle between those two vectors, is exactly 0? In that case, what we indeed have is the dot product of those two vectors, v and w, will be 0. And in this case, the angle theta be pi over 2. So we know the angle theta equals pi over 2. Means geometrically that the angle is a right angle, and then we can say the v and w, the two vectors, are perpendicular to each other or orthogonal to each other if the dot product of the two vectors is just 0. So the dot product is actually like related to the geometric information between two vectors. Okay, so let's look at this one example. So we want to find the angle between those two vectors, which are given here. So how do we do that? From the law of cosine, we can compute the cosine of the angle, let theta be the angle between the two vectors. Okay, and then the cosine theta will be obtained by the dot product of the first vector and the second vector divided by the length of the first vector times the length of the second vector. We know how to compute the dot product. We can list it here. Which is supposed to be a scalar, right, obtained by multiplying the corresponding components of the those two vectors. So it's 4 times 2 plus -1 times 1 plus. So those plus are very, very important. 5 times 1, which is 8, minus 1 plus 5, which is 12. Okay, so this is dot product. And we also need to find the length of those two vectors, right? This is supposed to be the square root 4 squared plus -1 squared plus 5 squared, which has 16 plus 1 plus 25, I think, which is a square root of, I think this is 42. And then the length of the second vector will be square root 2 squared plus 1 squared plus 1 squared, which is 4 plus 1 plus 1, which is square root of 6. So the cosine of the angle theta between those two vectors is indeed 12, the dot product, divided by the length of first vector, square root of 42, and then times the length of the second vector, square root of 6. And if you notice, we can simplify this. So square root of 42 is square root of 6 times 7. 7 times square root of 6 times square root of 6. So this is a 12 divided by square root of 7 times 6. So this is indeed 12 over 6 is 2, so 2 over square root of 7. This is what we have. All right, so there are other interesting problems we can handle also. For example, if we are given two vectors, one is specified by having all the 3 components, and the second one is having a free parameter c they need to determine. And the question is asking us to find this value of c such that those two vectors u and v are orthogonal. So the answer should be addressing this question. How do we know u and v will be orthogonal to each other? So if thinking, if u dot v equals 0, then u is perpendicular to v. We use this notation to indicate those two vectors are perpendicular or orthogonal to each other. Okay, so do we know the dot product of u and v? Yes, we do, because we can compute. So u dot v is, remember, 1 times 4 plus 2 times -3 plus 3 times c, which equals, I think the 4 minus 6 plus 3c, which is -2 plus 3c, and it has to be equal to 0, I think. All right, and how to make it a 0? So we need to have -2 plus 3c equals 0. So this tells us 3c equals 2. So this tells us c equals 2/3. So c equals 2/3. That's what we are looking for. Okay, let's just pause for a moment.